Hey guys, welcome back. Nachkazi here. If you ever wanted to become a routing ninja, this video is your opportunity. You're going to learn a ton about OSPF, or Open Shortest Path First routing protocol. I'm going to cover a ton of fundamental concepts, and I'm going to build on different concepts so you get to a level where you start off at a novice level, you then move on to the intermediary, and by the time you're done with this video, you're going to be at the expert level when it comes to CCNA. I'm going to cover all the different topics that the CCNA exam blueprint covers, and by the time you're done, you're going to be a ninja in real world. I am super pumped. Let's roll. Welcome to CCNA 200-301 course. Today I'll cover Section 3, Part 3, IP addressing and routing. We'll do a deep dive into OSPF. Here are the topics I plan on covering today. I'll first do a quick review of static versus dynamic routing. I will then get into OSPF basic concepts. Finally, I'll wrap it all up with OSPF command line interface configuration. So what's the difference between static and dynamic routing? First, in static routing, we have to manually specify the routes, whereas in dynamic routing, routes are dynamically learned. Second, in static routing, we have to specify a lot of manual entries for redundant paths. And because we have to specify, it's at least double the number of entries, but if you have more than 2 redundant paths, then most likely you're going to have to enter even more entries into your routing table by hand. That makes the process very error prone, because human beings, we make mistakes. And in static routing, you best believe that if you have nothing but static routing configured everywhere, you're going to end up making a ton of mistakes. Whereas on the dynamic routing side of the house, we have what's called built-in intelligence that calculates the best path to the destination. Because dynamic routing uses different mathematical algorithms, that's the built-in intelligence I'm talking about. Third, in static routing, if we have bad entries, that can cause routing loops. In dynamic routing, on the other hand, we have inherent routing loop prevention mechanism. 4. In static routing, we have a predictable path, meaning the route that we have specified manually, we will always expect the same route to the destination. It's never going to change. So we have predictability in path. Whereas on the dynamic routing side of the house, we have a predictable outcome, meaning ultimately what we care for is whether or not a particular source can get to a certain destination, because routing is all about source to destination, right? What's in between, like as far as different paths, we do care, but we could care less as long as we can get to our destination predictably. So dynamic routing gives us that ability. Number 5, static routing is for small networks, whereas dynamic routing is great for medium to large size networks. And finally, static routing is great if you're getting paid per routing entry, wink wink, whereas in dynamic routing, not so great if you're getting paid per routing entry, sad face, because you're going to have to type in less entries in dynamic routing, which means you're going to get paid less. Well, there's a pun intended here. Of course, nobody will ever hire you per routing entry. Most likely, you're either going to be a contractor where there's going to be a certain project you have to complete, or if you're a full-time employee, you have to learn how to do things efficiently, and that's where dynamic routing comes into play. Now let's look at OSPF basic concepts. First, OSPF overview. Shortest path first algorithm. So in particular, we're going to talk about OSPF version 2. It's defined in RFC 2328. It uses SPF algorithm, or shortest path first algorithm, also known as Dijkstra algorithm, to find the shortest path to each destination based on the cumulative cost. And we'll talk about the cumulative cost as we continue moving forward to get to a particular destination. That's what makes OSPF such a powerful routing protocol, because under the covers, it uses SPF. And by the way, not sure if you guys know, but SPF is the same algorithm that our GPS uses. So it's really, really cool. GPS uses the same mathematical logic to figure out how to get you to your destination in the most efficient way possible. OSPF is vendor neutral, meaning it's an open standard. So if you're on a Cisco router on one end and there's a Juniper router on the other end, they will work perfectly fine as long as they're running the same version of OSPF, which in this case is OSPF version 2. OSPF has a built-in intelligence for building a loop-free topology. OSPF pretty much guarantees a loop-free topology. What OSPF does is it only keeps the best routes in the routing table. If there are more than one paths in the routing table to get to the destination, OSPF supports ECMP, or equal cost multipath, and that allows OSPF to actually have redundant paths being installed in the routing table. OSPF supports VLSM and security. So if you guys recall from my previous videos, VLSM stands for Variable Length Subnet Masking, which means OSPF is classless, and with every single route advertisement, it advertises a subnet mask for that destination. And from a security standpoint, it can either use clear text or MD5 based authentication. Now, this is an optional feature. You don't have to use it, but it's recommended to use it to protect potential bad actors or hackers wreaking havoc on your environment by bringing in a rogue device that pretends to be an OSPF router and it's actually not. In real world, you would want to do it for security reasons. OSPF deals with efficient updates. OSPF advertises link states or connected links instead of routes. So the biggest difference between OSPF and other routing protocols is other routing protocols advertise routes or networks, whereas OSPF advertises the link states or the local links. OSPF sends incremental or triggered updates only when changes happen in the network rather than sending the entire routing table, and that allows OSPF to achieve really fast convergence, meaning when things change in the network, our network can very quickly adapt to that change. OSPF also sends periodic updates known as LS refresh or link state refresh every 30 minutes. And LS refresh contains a full routing table. Now let's quickly review the different type of tables that OSPF maintains. In particular, it maintains 3 different types of tables. First, neighbor table, same as EIGRP. OSPF routers use hello packets to discover neighbors. OSPF goes through a series of steps to form a neighbor relationship, and I'm going to go ahead and walk you through those steps momentarily. The next table that OSPF uses is called Topology table, and Topology table is a map or a roadmap of every single network that is available within the same area and all the possible paths to get there. And I'll talk about areas in a moment. Until then, hold that thought, but let me explain what topology table is. So, I'm right here in California. If I want to get to Texas, which is right here, there are different paths I can take. I can take Nevada, Utah, Colorado, Oklahoma. down to Texas. That could be path 1. Or I can take a different path. I can go California through Arizona, New Mexico, down to Texas. So I can either take the red path, the northern path up here, or I can take the southern path down here in blue. Well, the reality of the matter is, when I fire up my GPS, it's going to show me these two paths. Now, you may jump to the conclusion by looking at these two paths immediately to go, well, the blue path should always be preferred because you're only going through 2 different states, compared to the northern path in red, where you're going through 4 different states to get to Texas. But let's not jump to the conclusion here, guys, because there's a couple of very critical pieces that are missing here. Piece number 1, the source. What's the exact source of this traffic? Meaning, am I located in Southern California or am I located in Northern California? I'm located in Northern California, right? I'm in San Jose. So if I want to get to Texas, perhaps the northern path is faster to get there. Maybe. But if I live in Southern California, most likely the southern path is much faster and efficient. But there's one other critical piece that's missing. What does the traffic look like? That's another thing my GPS looks for, right? If the traffic is bad on the southern path, then most likely northern path is the only efficient path to get to my destination. Now, how's that relevant to OSPF? OSPF, using the SPF algorithm, or the shortest path first algorithm, uses the same logic. It looks at the source, it looks at the destination, and then it also looks at, instead of traffic, it actually looks at bandwidth. OSPF doesn't actually look at the congestion, but it looks at the bandwidth, which is considered cost to get to the network. Now, I'll talk about cost in a little bit, but the bottom line is that this is the information that OSPF uses to figure out how to allow packets to go from the source to destination in the most efficient way possible. Now, with this context in mind, let's continue. And there's a third table that OSPF maintains called a routing table. And where routing table comes into play is OSPF router initially builds a topology table right after the neighbor table is built. And once it understands the topology and the database is built, then it runs its SPF algorithm and it finds the best path, and then that best route goes in the routing table. Now here, let's quickly take a look at which path OSPF will choose to install in the routing table. We have the source on the left, router 1. We have destination to the right, router 8. Path A, there's only one hop in the middle, only one additional router in the middle. We have path B in green, and we have 2 routers in the middle, or 2 additional hops. And we have path C that has 3 additional hops to get to the destination. Which path do you think OSPF will take? Well, you might jump to the conclusion and say, obviously, path A, duh, that's the path with the least number of hops. But you would actually be wrong. And let me explain why. Path A, what if this is 10 meg? And this is also 10 meg. Whereas path B, what if this is 100 meg on all the circuits? And path C is 1 gig on all the circuits and all the links all the way across. Now, which one do you think OSPF should choose? Well, OSPF uses bandwidth intelligence to figure out, right? It's called cost. That's a metric that it uses. Obviously, it will take path C and install this path in its routing table to get to this destination of router 8 because of the efficiency in bandwidth. So hopefully, this gives you an idea that in network architecture, we can never jump to conclusions. We should take our time, look at the design, and see exactly what the network is telling us before we can jump to any conclusion. Now let's quickly look at OSPF areas and terminology. OSPF has what's called Area 0, and it's considered a backbone area. And the best analogy I can give you when it comes to the backbone area is the human backbone. We have a backbone that connects to all the different limbs in our body and all that. And all the signals are processed through our central nervous system and carried through our backbone to the brain. But our backbone is the key to connecting the entire body together, and that's exactly what OSPF Area 0 does for us. It's the backbone of the entire network. And all other areas must connect to Area 0. So let's quickly take a look at this topology we have here. So we got a couple of different routers here. We have an ASBR, ABR, BB, and ABR. And I'll explain this terminology in a moment. I'll just explain BB for now. BB stands for backbone router. And the reason it's called backbone router is because it's only in Area 0. But then we got other routers that have connectivity into other areas, which we'll discuss in a moment. But the bottom line is all areas must connect to Area 0. Routers in the same area share the same database or topology table. In other words, this router right here, this router right here, this and this, all four of these guys will have the same view of the entire network, meaning they'll see the same links being advertised, same networks being advertised. They're going to see the exact same picture of the entire network. The only difference is that each router is going to be at the center of the universe. Once again, it's a GPS idea. No matter where you are in the world, when you fire up your GPS, you immediately become the source. And then the place you want to visit is the destination. It's the same thing here. And ABR would be the source, and then when it runs its shortest path first algorithm to figure out how it should communicate with the rest of the network and the databases are exchanged, all of these routers will have the same view from their own unique perspective. ABR stands for Area Border Router. That's the router that sits at the border of the network and it connects multiple areas together. So if you look at, for example, this area border router right here, it has one leg into Area 1 and another leg into Area 0. If you look at this ABR right here, it has one leg into Area 2 and another leg into Area 0. So that's what makes these routers ABRs, or Area Border Routers. We also have an ASBR, which stands for Autonomous System Boundary Router, which in this case is this guy. So it has one leg into Area 0, into OSPF, and it has another leg into another external routing domain. Now this could be BGP, this could be EIGRP, this could be ISIS, could be RIP version 2, but I hope not. But the bottom line is ASBR connects you to the external world. When it comes to OSPF, we have this area concept. We have what's called a single area design, and we have what's called a multi-area OSPF design. Theoretically, you could get away with having a single area and all of the devices can be part of that area. So for example, you can have Area 0 and all of the devices in your network, let's say if you have 50 sites, all 50 sites can be part of OSPF and life is good. But what if your network grows? What if you have 100 sites or 200 sites or maybe 1,000 sites or 10,000 sites? Having a single area in that case would be insanity. So what you would do then is define different areas and somehow figure out like a geographical separation to define how the network is designed. And that allows an efficiency in the network. Another very important thing to keep in mind, guys, is route summarization. And it's a really amazing feature. And let me give you a quick example. So let's say behind this ABR, you have 30 routers. Okay. And each of these 30 routers has 3 different subnets on the LAN that are carrying different type of traffic, PCI, internet, and MPLS. So 3 times 30 equals 90. That's 90 LAN subnets that this ABR will have to advertise into area 0. But not only that, this doesn't even include all the links. So the 30 routers, each router is going to have at least single link. So assuming we only have a single link design, we don't have redundant circuits. That's 90 plus 30. That equals 120 potential networks that will have to be flooded into this area 0. Now, as you can imagine, if you have a much larger network, you're looking at a much, much larger number of advertisements. So to compress this, and instead of advertising 120 individual networks, wouldn't it be nice if you could take all these 120 and advertise a single network? And this is where network summarization come in. We can actually do that. It's called supernetting. It's the opposite of subnetting, where we take a bunch of subnets and we summarize them. In subnetting, we take one network and we divide it into different networks, right? But in summarization, we take multiple smaller networks and combine them into a single larger network entry. And this way, we don't have to send a ton of routes. We just send a single route and that's it. And one key thing to keep in mind is in OSPF, only the area border router and the autonomous system boundary router are the ones that can do summarization. No other device can do summarization. So in other words, this guy cannot do summarization. And if there was another router behind this ABR, or if there was another router behind this ABR, these devices won't be able to do summarization. And this backbone won't be able to do summarization either because it doesn't have a link in different areas. Only the device that sits at the edge of different networks has the ability to be able to do summarization, which makes sense. Now let's quickly take a look at OSPF LSA types. There are 3 different types of LSAs in OSPF. And these are link state advertisements. So when the routers connect with each other, they start exchanging packets with each other. That's where these LSAs come in. So we have what's called an LSA type 1. It's called router LSA. And it describes a router. Each router sends a type 1 LSA in an area, and it includes a list of directly attached links and a router ID. LSA type 2 is the network LSA, and it describes a network that has a designated router, and we'll talk about a DR in a moment. This LSA is only generated by the DR on broadcast network, and it includes the DR and BDR IP, subnet ID, and subnet mask. And finally, LSA type 3, called summary LSA, it describes a subnet in another area. This LA is summarized route generated by the area border router. It includes subnet ID, mask, and router ID of advertising ABR. Keep in mind, there are 11 types of LSA and OSPF. In CCNA exam though, because of the exam blueprint, we're only covering 3. When we get to CCNP, we're gonna learn about 4 additional type of LSAs, but it won't be until you get to CCIE that you'll get to learn about all 11 types of LSAs. Now let's quickly dig deeper into the OSPF header. And within an OSPF header, there's a field called packet type. And let's zoom into that field within the OSPF header, also called LSAs or link state advertisements. What that packet contains is a hello message. That's what's responsible for neighbor discovery and neighbor adjacencies. These messages are sent to multicast address 224.0.0.5 or 224.0.0.6. Now let's pause here for a moment. I want to describe a very important concept here. Instead of doing a broadcast to all the devices, what OSPF does is it uses multicast to send hello messages. So let's say if you have all these different routers that are connected to the same LAN segment, and this router right here is only doing static routing, and so is this guy. Both of these guys are doing static routing, whereas these guys are running OSPF, these three right here. Well, because it uses multicast, only this router, and this router is gonna get the hello message. These two routers running static routing will never even get this hello message, and they shouldn't because they're not running OSPF. That's why multicast addressing is used instead of a broadcast, because broadcast would be sent out to everybody. Even the static routing devices will get it. But in this instance, they won't because you're using multicast. The next type of packet that OSPF uses is called database descriptor, or DBD. It's a link state database summary. The third is link state request, or LSR. It's the request for specific networks, and it's a unicast. LSU is a response to an LSR, and it contains multiple LSAs within it. So you can think of an LSU as like a bucket. And within that bucket, you got a whole bunch of LSAs. And finally, we got link state acknowledgement packet that is designed for acknowledging the database descriptor packet, the link state request, and link state update. And this is what makes OSPF a reliable routing protocol. Now, if this doesn't make a lot of sense to you right now, hang in there with me as we continue exploring additional topics. This stuff will make sense, and we'll come back to it, especially when we're doing the CLI configuration piece of things. This stuff will start to click. Here's a quick overview of OSPF neighbor adjacency formation process. So let me quickly explain. So we got a router on the left, R1, and we got router on the right, R2. Let's imagine these two routers are directly connected with each other with a piece of copper cable. Here are the steps these devices will go through in order to form an OSPF neighbor relationship. Step 1 is when the routing process is actually running on the router, but we're in a down state because we haven't learned about our neighbor yet. Step 2 is called init state. And this is where router 1 would send a hello message to router 2, also known as initialization state. Step 3 is when router 2 will respond back to router 1. And in that hello message, router 1 will actually get its own router ID back from router 2, like a boomerang. And when that happens, it achieves what's called a two-way state, meaning it now knows that I have a neighbor who has acknowledged my presence, so now you can start talking to each other. Step 4 is what's called an X start state, and this is where the DR and BDR election takes place, and the highest router ID becomes master. Now, let's park it for a moment. I'm gonna go deeper into this momentarily. Once we get past that step, we'll get into step 5, which is called exchange state. Here is where the database descriptor, or DBD packets, are exchanged. Step 6 is the loading state. Based on that database descriptor packet that was exchanged in the previous step, the router sends an LSR, or link state request. In this case, R1 will send an LSR to R2, and R2 will respond back to it with an LSU, or link state update, that contains multiple link state advertisements within it. And then the final step, step 7, called full state. Here all the LSAs are exchanged and OSPF databases are fully synchronized. Now let's quickly take a look at OSPF network types. The two network types that are covered in CCNA are broadcast network type and point-to-point network type. Let's first speak to the broadcast network type. That's a default mode on all Ethernet interfaces. It requires neighbors to be on the same subnet. It's used for auto neighbor discovery, and OSPF hellos are sent to 224.0.0.5. DR and BDR election takes place in broadcast. And when we have DR and BDR, then those hellos are sent to 224.0.0.6. And we'll talk about that in a moment as well when I go deeper into the DR BDR process. Couple of things to keep in mind. Highest OSPF interface priority wins the election. By default, all the interfaces have a priority of 1. So because interface priority is always the same, router ID ends up becoming the tiebreaker. Once the DR is selected, DR is in charge of receiving and sending all the updates to everyone on the local subnet. After the DR and BDR election, all other OSPF routers on the local subnet become DR other. And there's another network state that I think is important for you to understand called point-to-point network type. That's the default mode on serial interfaces. So if you guys are familiar with T1 or E1 in Europe, or OC interfaces here in the US, or STS interfaces in Europe, or APAC, then you know what serial interfaces are. And serial interfaces are, by default, considered point-to-point because there are no additional devices. There are only 2 devices on a serial interface. Hence the reason we call it point-to-point. It requires neighbors to be on the same subnet, uses auto neighbor discovery, and hellos are sent to 224.0.0.5. However, the big difference here is there's no DR or BDR election because the broadcast is not supported on serial interfaces or the point-to-point network type. Now let's quickly look at OSPF DR and BDR. So everything that we have learned up to this point would help us understand how this works. So let's quickly jump in. So if you look at this network segment here, this is a point-to-point link because this is a serial link, right? In this case, what's going to end up happening is there is no DR or BDR happening here, right? Because it's a serial link and we just talked about it. So this is a point-to-point. However, we are going to have a competition on a couple of different segments. First of all, this right here is a shared segment. So these 2 routers are going to go through the election process. Let's assume this guy becomes the DR, this guy becomes the BDR, and do you guys remember the third type? It's called DR other, or druther for that matter. And then there's another election process that's going to take place here on this segment. Let's assume this becomes a DR, this becomes a BDR, and all these guys become DR others. So that's how this whole DR and BDR process works. But what's the reason behind DR and BDR to begin with? Well, in OSPF, what ends up happening is when we're exchanging our databases, which is called the LSDB, link state database. When we're exchanging the database, we assume full mesh connectivity, meaning all of these routers can talk to each other and they can all send updates to each other. As you can imagine, this could become very chatty if everybody started sending updates to everybody on the same LAN segment. So what ends up happening is with the DR and BDR election, let me clean this up a little bit. If this guy is the DR and this guy is the BDR, by the way, BDR only comes into picture when the DR is down. So BDR is there, but it's not actually doing anything. DR on a LAN segment becomes in charge of everything. So what that means is if there's a change on this LAN segment, if something happens here, this guy is going to advertise it to DR. DR is going to receive that update, and then the DR would be responsible for responding to everyone. Instead of this guy sending the update to this guy right here, this router, and then this guy advertising it to everybody else, and then everybody else advertising it to everybody else. This chaos is controlled by this DR, and this DR then becomes responsible for letting everybody else know. And the criteria for the election is the highest interface priority. If that's not configured, then the highest router ID will end up becoming a DR or BDR. Now in real world, typically the best practice design would be to use the interface priority as a tiebreaker, because then you know for sure that, for example, if you want this guy to be DR no matter what, if you set up the interface, this interface right here with the highest interface priority, then this guy will always be preferred no matter what. And one last thing to keep in mind is on a shared network segment, all routers except DR and BDR stay in two-way state. And we talked about states a little bit ago. Now let's quickly talk through the OSPF metric called cost. So once the neighbor adjacency is done, like we talked about a moment ago, OSPF runs its SPF algorithm to find the best path to the destination. And to find the best path, it uses a metric called cost, and it's based on interface bandwidth. And the formula is cost equals 100 divided by bandwidth in megabits per second. And here's the default OSPF cost table. So as you can see here, if you guys remember the 56 and 64K modems, these are the default costs. T1 is a cost of 64, E1 is a cost of 48, Ethernet 10 meg is a cost of 10, FAST is 1, Gigabit Ethernet is 1, 10 gig Ethernet is 1. And as you can imagine, if you let this default table operate, that's not a good thing, because in today's data centers and networks, you may actually have 100 gig links. And if the 100 gig is the same as the fast Ethernet, well, we got a problem, right? So there's actually a way to fix that. We'll talk about it in a moment. And here's a quick topology of how this can play out. So as you can see, the different type of links, this is 48 because this is an E1. And this right here is 1785 because this is the 56K circuit. And this guy's 1 because it could be 100 meg circuit. This could be 1 gig, so on and so forth. Now, if you wanted to change it, which we would want to, we can change it under the routing process, under OSPF routing process. We'll type in the command auto-cost space reference-bandwidth space. When we type in 100,000, this means 100 gig. The minute we do that, 100 gig becomes a cost of 1, and all the other subsequent bandwidths like a 40 gig, 10 gig, they will have higher costs than 100 gig, and this will truly reflect what our environment looks like. So remember, OSPF has been around since 1980s. This is where these values are coming from, and we'll have to make changes for this to work. Here's another way of specifying cost at the interface level. You can type in IP OSPF cost and then the cost of 1. Remember, cost of 1 is most preferred. And one last thing I want you guys to keep in mind is once you change the reference bandwidth command, it must be adjusted on all OSPF routers. So you cannot type in this command on just one router and be done with it. You're going to have to specify it on all OSPF routers in your environment so they can calculate and run their SPF algorithm accordingly to find the best path around the network. Now let's quickly talk about one more item before we get into the CLI. And that is OSPF neighbor adjacency requirements. Now, here are the 10 commandments of OSPF neighbor relationship. And what I mean by that is you must abide by these 10 rules to make sure the neighbor adjacency comes up. First one is interfaces. Interfaces must be in an up-up state. Now, it's one of those where you go, duh. I mean, of course you have to be in an up-up state for the routers to talk to each other. Second, no access control list filtering routing protocol messages. So the second one means you shouldn't have any ACL on an interface that is actually filtering the routing protocol messages, because that would make the adjacency not come up. Third, interfaces must be in the same subnet. That makes sense. Authentication must match on both ends. Makes sense. Hello and dead timers must match. Each router ID must be unique. So you cannot have two routers on the same network with the same router ID. It's going to cause issues. And your OSPF adjacency will flap or may never even come up So make sure each router in your environment has a unique router ID. Interfaces must be in the same area. OSPF process should not be shut down. Duh. All neighboring interfaces must use same MTU setting. So that's another important one. Here, the OSPF adjacency will come up, but you're going to have weird type of intermittent issues if the MTU mismatches on the two neighboring interfaces. So make sure your MTU value matches. If it's 1500 bytes on one side, then on the other side of the link, it should also be 1500 bytes. And finally, all neighboring interfaces must use the same OSPF network type. It's another one of those scenarios where if you had a mismatch, the neighbor relationship is going to come up, but then you're going to have bizarre issues where the information will never make it into the routing table. Things will get lost into building the LSDB or the link state database. So keep this list in your back pocket. Now let's quickly jump on CLI, my favorite part, and talk about OSPF and actually get to see it in action. Love getting my hands dirty. When it comes to routing, there's no better way to learn. Now let me give you a quick walkthrough of this lab right here. We have two routers in the middle, router 1 and router 2, part of area 0. We have router 3 in area 1 and router 4 in area 2. Now if you start from left to right, we got network 10.0.31.0/30 between router 3 and 1. We got network 10.0.0.12.0/30 between router 1 and 2. And between router 2 and 4, we have network 10.0.13.0/30. So I want you to familiarize yourself with this. And I've also specified the ending IPs on each side of the link, so you know exactly how that's going to pan out. And on router 3, I've got a bunch of loopbacks that are defined. And these loopbacks are representing different type of networks or subnets that are behind router 3. And similarly to the right on router 4, I've got a ton of loopbacks that are representative of different subnets or networks that are behind router 4. With this context in mind, let's quickly jump into the CLI. So let's quickly take a look at router 3 first. And let me show you what I've done. So I've configured the 10.0.31.2 IP address on router 3's interface. And let's make sure I have the correct subnet mask on this interface. I'll do show run pipe section interface and hit enter. This is a cool command. Instead of running through the entire show run or running config, you can just simply look at the different interfaces. And by looking at fast Ethernet 1/0, I can see that I do have /30 specified on this interface. Let's also quickly take a look at show CDP neighbor command to see who's directly connected with me. And as you can see here, as depicted in the diagram up above, router 1 is indeed connected with me over my local interface of fast 101/0, and the remote side is also fast Ethernet 1/0. So that is great news. Let me go ahead and enable OSPF on my router here. And what I want you guys to understand is that when it comes to OSPF, the way we enable OSPF on the router is by simply typing in router OSPF and then the process ID. And when we do that, we're now under the OSPF routing configuration mode. Now let me take a quick pause here because I think it warrants a quick explanation. You see this OSPF process ID? It's locally significant, meaning it's not carried through the OSPF LSA update or anything. It's only enabled locally on the router And that's about it. Now what we need to do next is we need to define the interfaces that I want to enable OSPF on. I'm going to give you a couple of different ways of doing this so you guys can become the masters of OSPF. Okay. The least specific way or the laziest way is you type in network 0.0.0.0 and you type in a wildcard mask of all 255s and you type in area 0. Now, I said wildcard mask and you might be going, whoa, hang on a sec. What's a wildcard mask? And that's a great question. Let me quickly do some whiteboarding so I can explain what a wildcard mask is. So a wildcard mask is considered the mirror opposite of a subnet mask, and it's also known as an inverted mask. Okay, so let me explain. So if you guys remember from the videos that I did on the topic of subnetting, what is this? This is a /24, right? /24 is represented as 255.255.255.0. What would be, this is called a subnet mask, right? But if I wanted to create a wildcard mask from this, how would I go about doing that? Well, it's the mirror opposite. So that means where I see 255, I will actually specify 0. 0, 0, and where I see 0, I'll specify 255. So once again, wildcard mask is the mirror opposite of the subnet mask. And wildcard mask is used by EIGRP, OSPF, and also access control lists or ACLs. So it's something important that you have to understand and learn, and to continue building on it. In subnet mask, where we see all ones, so for example, going back to 255.255.255.0 example, if I were to zoom into this, we have, you know, if you guys remember the handy dandy binary conversion chart, I'm gonna go ahead and specify all these values here. And these are the different binary bit positions, and in 255 means all the bits are on. So every single bit is on. And when we add up all these numbers, that adds up to 255. Now I've done a detailed video on this topic. Go ahead and check that out. It's called IPv4 addressing and subnetting. Now, that being said, in the subnet mask, wherever we see ones, that means we care. That means we actually care for these bits. And where we see zeros, like this 0 right here in the last octet, if you were to zoom in, that would be all zeros from a binary perspective. That means we don't care for these bits. We do care about the ones, but we don't care about the zeros. Now, what happens in a wildcard mask is the opposite of the subnet mask. So in the wildcard mask, the logic is reversed, meaning wherever I see zeros, that means I care, and wherever I see ones means I don't care. And that's the wildcard mask for you. Let's go ahead and jump back on the CLI again. I could do it this way, but I'm not gonna do it. This is the laziest way of doing it. And I'm gonna go ahead and type in no in front of this command and remove it. Now OSPF is not running on any network. I'm only running a local OSPF routing process, but I need to be able to start running it on interfaces. Now, the next level up is less specific, but here what we can do is we can go network 10.0.0.0 and with a subnet mask of 0.255.255.255 area 0. And I'm actually doing it wrong. I shouldn't actually be saying area 0. I should actually be saying area 1. So what that means, I'm going to go ahead and have to type in no in front of it, retype this command, and put 1. Because remember, looking at the diagram, I'm in area 1 on router 3, right? So I have to specify area 1. Now what this command is doing is that, as I explained earlier, it's saying all I care for is the first octet, because that's a 0 on the wildcard mask. This means I care, but then the rest of the 3 octets, I do not care because I've got 255.255.255 there. So wherever I have 1s in the wildcard mask, I don't care. Meaning, when I take this interface right here, and as long as the first octet matches, I'm going to go ahead and enable OSPF on whether I have 1 network or if I have 10 different networks. I'm going to go ahead and enable OSPF on all these different networks. And this should be fine. We can do it this way, even though I would prefer this to be more specific, but that's good enough for demonstration purposes. Now let me go ahead and jump on router 1, look at show IP interface brief here, and see what it's got going on. I'll do show CDP neighbor to see whether or not I'm seeing the appropriate devices, and sure enough, to the left of router 1, I'm seeing router 3 connected, and then to the right, I'm seeing router 2 connected. That's beautiful. Let me go ahead and enable OSPF on this router. So I'll do config T router OSPF 1. By the way, it doesn't have to be process 1. This process ID doesn't have to match. I can call it process 100 if I wanted to. And as a matter of fact, let me call it 100 so I can demonstrate my point that this value right here is irrelevant. It doesn't really matter. It's something locally significant. It's not carried in LSA updates or anything like that. So I'm going to prove my point in a moment. Let's go ahead and now let's be a little bit more specific this time around. We're going to say network 10.0.31.0, and we're going to go 0.0.0.3 for the wildcard mask. And if you're wondering, where did I get 3? I'll have to explain that to you in a moment. Thanks for sticking around. By the way, there's a lot more to this video than what you have seen. In order to watch the entire video, you're gonna have to be a little patient because I'm working on designing an entire CCNA course. I'm gonna do an official launch in the next couple of months, but until then, I'm gonna keep putting little nuggets of the CCNA exam out there on my YouTube channel until the course is ready to be published. Hope you enjoyed today's video. If you did, give me a thumbs up, hit subscribe, and I'll see you in the next video.